Right, welcome to another Orbiter 2016 video. This is going to be a bit of fun more than anything else, using the Python Jupyter Notebook widget for calculating low thrust burns. I'm actually going to apply it to a little scenario which has always intrigued me, which is the sort of the Mark Watney scenario, where Mark Watney, if you've seen the film The Martian, Mark Watney, the protagonist of the story, has to get off the ground and rendezvous with a vessel which is presumably in a hyperbolic approach orbit to Mars. And he has to time his rendezvous with the approaching vessel, the Hermes, with some degree of precision. It has to approach within a few hundred meters and within 10 meters per second speed differential. And the question is, can we use the Python widget that we prepared earlier, or used earlier for calculating low thrust burns, to help us with this particular scenario? As it turns out, yes, we can. And to illustrate this, I've set up a dummy scenario where we have a Hermes equivalent. It's actually the ISS transported to Mars by the miracle of the scenario editor. If I can just circle around here somewhere, we should be able to find Mars. Or there we are, there's Mars. So we are on a hyperbolic approach orbit to Mars. We're going to have one and one only encounter with Mars. Closest approach is going to be 350 kilometers, and when we get there, our periapsis velocity is going to be 9.3 kilometers per second. Okay. Now, we've also got parked in a circular orbit a delta glider, which is hopefully going to rendezvous with the our Hermes equivalent as it passes by Mars. And we want to try and get a precise encounter, set up a precise encounter. I've actually gone through and set the orbit up so that it does work, but what I want to do is to show how I set it up using the widget, the Python widget, and also then just demonstrate that indeed it does yield a rather good solution. So it sort of solves the Mark Watney problem, at least from a low Martian circular orbit coplanar with the approaching Hermes hyperbolic orbit. Not quite the same thing as the Martian scenario, but good enough for the purposes of this. What I want to start off with is just basically to point out the things that I do know about the orbit of our Hermes equivalent, the ISS. It's got a periapsis altitude of 350 kilometers, as we said. Its orbital eccentricity is 6.5528. Yep, no units. The velocity that we will have when we get there will be 9.3 kilometers per second, the periapsis. Our V infinity, our hyperbolic excess velocity, is going to be a whopping 8 kilometers a second, 7,974 kilometers per second. And this is by no means an unrealistic scenario for an approach to Mars, where you basically want to fling off and have a later encounter with Earth. It's part of some time ago I did some Aldrin Cycler calculations, and numbers of this magnitude were quite common. You can have slower approaches, but this is a fairly representative speed of approach to Mars, and you have to go from low Earth orbit, where your orbital speed is, let me see, 3.4 kilometers a second, and rendezvous with the approaching Hermes equivalent at something around about 9 kilometers a second. So you have to make up the difference of 5.5 kilometers a second through some kind of escape burn, and you have to get the timing correct. We also know that the inclination of this orbit is 5 degrees and the longitude of descending node is 27 degrees. These are round numbers, and I set up the scenario so that they were round numbers. In addition, I've set the argument of periapsis of the orbit to 0 degrees, simply for convenience, and we know the periapsis date the data upon the MJD date for when we arrive at periapsis in our Hermes equivalent of MJD 51982.029096, and yes, all 6 decimal places are needed for this calculation to work effectively. Okay, so that's what we know, and finally we can calculate from this data the mean longitude of the cycler at periapsis, and that would be 27 degrees, and we'll come on to use that particular number a little bit down the track. Now, if I load up, nope, wrong thing, go back. Sorry, let me just go over to here and transport it over to this screen. I've made a copy of the Python workbook for escape plans, and let me just reset and clear the output so that I know where I'm starting from. I load in the standard packages, I load in my user-defined functions that I need to solve the problem. Now we come on to the scenario data. We now have a mu, which is the gravitational constant. I'm just going to pause if you don't mind, but this is going to go on for a fair bit of time, and although our Hermes is, we're basically, this is going to take a little bit of time, and I just don't want to run over time, so I'm just going to pause the orbiter for the time being. Now, if I go back to the workbook, the gravitational constant is now the standard g that orbiter uses, multiplied by the mass of Mars that orbiter uses. So the product is gm, or the gravitational constant mu, and that, because we've got an escape from Mars, we want things to refer to Mars. Now, what I want is to execute, I'm starting in a circular orbit of some radius, some altitude above Mars, and I don't know exactly what it is. I'm going to guess for the time being that the radius is 3,700 kilometers. And what I want to do is work out, adjust that number, the starting orbital radius, so that when I finish my burn and match the v infinity speed of the Hermes as it goes by, that the periapsis altitude of my final hyperbolic orbit will be exactly 350 kilometers. And I can only really, well, I can set up Python to do this automatically, but it's just as easy to do it manually. I'm going to guess at an initial radius of 3,700 kilometers and see how that goes. I put in the a fully loaded Delta glider, which has got a mass of 24,500 kilograms. We're not going to raise the question about how it got into orbit fully loaded, but nonetheless, just for convenience, we're going to use 24,500. The effective exhaust velocity of the vessel is the standard 40,000 meters per second that Delta glider uses, and we're going to require, for this burn to work effectively, we're going to require as much thrust from the Delta glider engines as possible, so we're going to use the default value for this particular scenario of 8 kilograms per second. We have to make up roughly 5.5 to 6 kilometers per second in a short period of time as we leave our circular orbit in order to catch up, as it were, with the Hermes. And there's no point in applying low thrust technologies to this problem. We'd need a big, hefty, powerful engine in order to get us to the Hermes quickly. Mark Watney is there in his convertible space vehicle. The only oxygen he's got is really the stuff is the oxygen in his suit. Limited supply, so we need to get him there quickly. The v infinity, the target hyperbolic excess velocity of the Hermes, is to go by. We know this from the orbital parameters of the known Hermes approach orbit, and that's 7,974.14 meters per second. And that's just copied over from what we know over here. We also know the cycler periapsis date. So this is going to be 51982.029096, which is this number over here. So I'm just going to hit return, shift return to load that data into Python. And then I'm going to guess that the burn is going to be 300 seconds. Could be wrong, could be something else. It almost certainly will be something else. I hit shift return again, and I get Python's solution. The duration of the burn will not be 300 seconds, it will be 423.03 seconds. And yes, the 03 bit does actually matter. If you think that the Hermes is approaching Mars at about 9 kilometers a second, if we are out by 1 second in our launch timings, we will be out by 9 kilometers. If we are out by 1/10 of a second, we will be out by 900 meters. So to get below 100 meters precision, we actually need 1/100th of a second accuracy in starting our burn, ideally. The amount of dV that we require is 5,946.147 meters per second. And our orbital periapsis at the end of the burn will be 349.44 kilometers. So our guess that we put in of 3,700 kilometers for an initial orbital radius for our circular orbit wasn't too bad. We're actually only off by 560 meters. So let's go back and do this again and lift things up by 560 meters. We'll amend R0, the initial radius of our circular orbit, by 560 meters, and we'll run this thing again. Not a whole lot has changed. Our orbital periapsis at the end of the burn is 349.99. So if I really want to be fussy, I can lift that up another 10 meters. Let's do it. Put that in 5.7. And go again. And there you are. Our orbital periapsis at the end of our burn will be at 350 kilometers. We need to start this burn 162.21 seconds before we get to the point in our orbit that coincides with the periapsis point of the Hermes closest approach. And we're going to rendezvous with the Hermes when our orbital altitude is 4,220 kilometers. Sorry, our orbital radius is 4,220 kilometers. Yeah. And the ideal MJD of the start of our burn is 5,100 MJD 51982.026816 to 6 decimal places. Okay, so basically we have our burn parameters, and we require an orbital radius for our circular orbit of 3,700 kilometers, and then a bit of change, 570 meters. We're going to require a circular orbit because all of this this Python widget always requires a circular starting orbit. We're going to set the same inclination and longitude of descending node as the approaching Hermes equivalent, which has got an inclination of 5 degrees and longitude of descending node of 27 degrees. And then we know two things that help us get the timing in our orbit correct. I finished now with that calculator, so we can put that away. We know that we need to start the burn 161.21 seconds before we arrive at the cycler. We know that we're in a circular orbit, so that works out to being starting the burn when we are 8.5440 degrees before the periapsis, when we are coincident with the line, the periapsis line. And because we know that our mean longitude, so this means that we need to start the burn when our mean longitude is 27 degrees, which is the mean longitude of the Hermes orbit when it's at periapsis, and 8.5440 degrees. So we need to launch when our mean longitude, the mean longitude of the Delta glider in the circular orbit, is 18.46 degrees. And we need to set things up so that it gets there on a very particular time, which is MJD 51982.026816, which comes from some fairly elementary calculations of circular orbits. Okay, now rather than set this up manually using Scenario Editor for you, or worse, launch from some point on the surface of the planet and get into the circular orbit with these right parameters. I've cheated, and I've just set it up so that it is in a circular orbit with the right orbital radius, with the right inclination and longitude of the descending node, with the right mean longitude at precisely the right time, so everything just works. And all we need to do now is set up a burn in a prograde orientation, locked into the prograde orientation using an autopilot. That lasts for, if we go back to our Python spreadsheet or a workbook, that lasts for 423.03 seconds, during which we will burn 5,946.2 meters per second of fuel, and we should rendezvous at the end of the burn almost precisely with the approaching Hermes equivalent / ISS. Okay, let's just close that down again, and let's go and boot things up, take orbiter out of pause. We are currently in the ISS point of view. We really want to go over now to the Delta glider, which is currently in a parking orbit. So we'll go over to ship, select GL02, go apply, and you can see that we're in a circular orbit with a radius of 3,701 kilometers, which is the target orbital radius that we want for our initial starting orbit to rendezvous with the Hermes equivalent. Our eccentricity is indeed 0, so we are indeed in a circular orbit. Our inclination is 5 degrees, our longitude of the descending node is 27 degrees, and currently our mean longitude, which is this last number down on the bottom line here, is 299. So we want to start the burn, our escape burn, or rendezvous burn I should say, when the mean longitude, this number right down at the bottom, gets to 18.46 degrees. Before we do that, we need to do a little bit of housekeeping. Let's get up the other MFD on the other side, select Pursuit MFD, and then just click hold to lock us into the prograde orientation. We are pretty much there already, but we'll just, so it really isn't going to burn any fuel to maneuver into that orientation, so I don't really need to redo any calculations. Let's just double check using scenario editor that indeed we do have a full tank, a full Delta glider. Yes, the mass of our vessel is 24,500 kilograms, which is what we require. That's all done. Let's set up a target in orbit MFD on the left hand side. Let me just move that out of the way. So let's go target again. Spacecraft is it's the Hermes, but it's called here the ISS. We'll put that in, and let's just go mod, turn off all the numbers, and we can see what's happening. The green line here points to where we are in our circular orbit, and the yellow line is pointing to where the Hermes is in its hyperbolic approach orbit, and it's way down off the screen. And our rendezvous point is going to be somewhere over here. Let's turn some of the numbers back on again. All right. So we've got our Delta glider in the right orbit. This is a bit of a piece of magic that I've done offline, but I've just walked you through the spreadsheet. The Python workbook to show you the basic generation of the numbers that have been used to develop the scenario. And I've just saved you from the tedium of setting up the scenario, using the scenario editor to set up the circular orbit exactly as per that plan. Okay, the last thing that we really need to do is to set up the burn timing, and we're going to use burn time MFD for this, and we're going to use basically set the estimated burn time to the amount of time that we know this burn should take, which is 423.03 seconds. Now, I've done this scenario a number of times, so I'm just going to put in the DV amount, which is, I've forgotten it. I'm going to go for 5934.4. Yeah, 423.03 seconds. How does that tally with our target? Well, it's the same, 423.03 seconds. So burn time MFD is now set up so that the estimated burn time matches the planned number coming out of the Python workbook. Okay, we're pointed our prograde, and we're locked in place by pursuit MFD, and I know that we're in the right circular orbit with the right radius, and we've got the timings right, so that we are going to hit this magic number of mean longitude of 18.46 degrees when the MJD gets to be 51982.026816. We're not quite there yet. So, time for a bit of time warp. Let's go up to 10x, and let's go up to 100x. And we'll keep on going for a little bit further. Getting close now. Right, back to real time briefly. We know that we need to execute the burn at 51982.0268. We're getting quite close now to this number. We're not going to use the MJD date as the trigger for setting the burn. We're going to use the mean longitude here, which gives us a bit more precision in setting up the burn. I'm going to turn off the visual display and just focus on the numbers here. When this number gets to be 18.46, then we execute, hit the burn button on burn time MFD, and we are away on a rendezvous with the approaching ISS/Hermes, and we will burn 6,000 meters per second, give or take, of fuel to get there. Okay, so let's just do a little bit of time warp. 10x. This is to be done fairly precisely, so I'm just going to concentrate on getting this right, and I'm going to do my usual trick of coming down to 0.1 time warp for the last little bit, just so that I can get the final digits on the start of the burn correct. So up to 16 degrees, we're going to get up to 18.46. 2 degrees to go, won't take very long. Very close now, 1 degree away. Okay, about 1/10 of a degree away. I'll just let that count through slowly. 18.46 is the magic number. 42, 43, 44, 45, and burning. I think I might have started just a little bit early. Doesn't really matter. Okay, go back to real time. Now this burn is going to last 420 seconds, so about 7 minutes. I'm going to do it in real time. Why not? I'm going to go outside because the view is a bit better. And in principle, I'll show you what's going to happen. I'm just going to close the nose cone because it's a little looks untidy with it being up. That's not going to hurt anything with it being up, but nonetheless, it's been left open and I want it closed. Okay, let's go and open a few external MFDs. Let's go for docking. Nope, yep, that's right. We want to target the ISS. And there we are. It's currently the ISS. Let me just increase this up a little bit in size so we can see it. The ISS is about 850 kilometers behind us. And to show that it is indeed behind us, let me just get up another external view. Orbit MFD is just fine. Put that down here. Target the ISS. And once we go into a hyperbolic state, we'll see that our green line is here. It's approaching this periapsis point for the Hermes orbit, and the yellow line points to where the ISS is at the moment, and it is indeed considerably behind us. Now it's going to catch up. It's doing, relative to us, currently doing 4.2 kilometers per second speed. So it's catching up with us at 4.2 kilometers a second, and it's 600 kilometers away. So it's only 600 kilometers. It's not really going to take very long for it to make up that distance at all. All right. What else? Can we see the ISS? No. I've set the tags on vessels on, so if we just scroll back up again, you see that GL02 is being as a tag attached to the Delta glider. There's a similar tag for the ISS, but it's just currently too far away for us to be able to, for it to register in the orbiter system, and it won't be really until we get down to about 50 kilometers away from us that it'll actually pop up on the screen. But somewhere out there is the ISS, and it's racing to catch up with us at the moment at quite horrific speeds. When you think about what's going on here and the sheer courage that you would have to have in order to execute a maneuver of this kind, you really have to marvel at the proposed Aldrin Cycler schemes or anything like it. If you launch and you make mistakes in this rendezvous sequence, that's it. You die. There really isn't much margin for error. The speed differential is 6 kilometers a second, and you've got to get this thing right to within really very small tolerances. You have to be a brave person indeed to embark upon this maneuver. But in this particular case, it's all going to turn out well, and it's really quite fascinating to watch, as it turns out. Okay, the Delta glider is currently accelerating at about 1.5 G, not particularly high acceleration. The MAV in the Martian, I think, it was sufficiently high acceleration to cause Mark Watney to black out, so we're looking at something around 9 to 10 G. So this is a relatively mild acceleration in comparison with that particular scenario, and I haven't tried to emulate that particular example. The distance of the ISS/Hermes is now just 110 kilometers, and the speed differential has now dropped from an initial, 5.5 kilometers per second down to a mere 1.7 kilometers per second. We're still approaching pretty darn fast. If we go over to orbit MFD, we just increase the size of this momentarily, you can see that the green and yellow lines, radial lines, are beginning to converge, and our hyperbolic orbit is beginning to overlay onto the ISS's orbit. So that's all good. Right, the ISS / Hermes, this is now 53 kilometers away from us. It's still catching up, and momentarily we should see the ISS appear. And there it is. So let's just move that around a bit. The ISS is indeed behind us and catching up. It is 35 kilometers away, moving at 1 kilometer per second speed differential. Our altitude above Mars is now 630, 640 kilometers. Our vertical speed is something in the order of 2 to 2.5 kilometers per second. This is no simple or mean rendezvous sequence. On Earth, if you're rendezvousing when you're in a low Earth orbit, is quite straightforward. You get lots of choices. Speed differentials of the order of hundreds of meters per second, not 6 kilometers per second. This is quite a different ball game. Anyway, the ISS is now just 3.8 kilometers away from us, traveling at 250 meters per second. We're coming up to the end of our burn. 1.3 kilometers away, 1.2 kilometers away, 900 meters. Ooh, this is going to be close, isn't it? And there you are. 600 meters away, and the speed differential is 0.13 meters per second. So that's not too bad. Now, if I got the timing right, if rather than just relying upon the numbers on the orbit screen, and if I set up a little Lua script so that the timing start of the burn was spot on, I would have got a lot closer to the ISS at the end of the burn, but that's not too bad. Okay, let's close out those. And I'm not going to do the docking procedure in this particular instance. I mean, I'm sure that people out there are capable of doing that, but the speed differentials are so low that really it's not a hard task to perform the rendezvous. And I really want to be outside, and I'm just going to do a bit of time warp to show you that indeed we are departing away from the from Mars on a hyperbolic orbit. And there it goes. We'll come back to real time, just rotate down, and the ISS is still there just below us, probably about a kilometer away. And there you have it, a rendezvous, or Mark Watney style rendezvous with a Hermes equivalent. It's not an easy maneuver to perform. I've shortcutted the thing by setting up the Delta glider to be in the right circular orbit to begin with, but I did do all of those calculations using the Python escape burn calculator widget. So it's not a complete fudge, but I just didn't explain all of the steps that led up to setting up this scenario. Okay, thanks for watching. Bye.